All right, hello class, and welcome back to Lecture 9, Part C. So in the previous lectures, we considered almost entirely the problem of coplanar orbital maneuvers. In this Part C and Part D of Lecture 9, we're going to somewhat briefly consider the problem of non-coplanar transfers, that is, maneuvers from one orbital plane to another. As I mentioned, these are the least energy efficient maneuvers we have because the energy of the orbital plane or the orbit doesn't change from one orbit to another, and yet the delta V required for that change can vary quite a bit. Similar to the case of the orbit in time, the transition to three-dimensional problems requires some additional development of mathematics, and in particular the problem of spherical trigonometry, which we'll address in some moderate depth. So to begin, in this relatively brief part, I'm going to introduce the problem of the first orbital 3D plane maneuver, which is the one you use to get off the ground, which is a rather large one. It's a typically about 9.3 kilometers per second maneuver, in that you have to establish yourself in orbit. If, however, you mistakenly establish yourself in the wrong orbit, these orbital planes can be quite costly to change, especially since you're moving at about 8.6 kilometers per second. And so those plane change maneuvers become suddenly very costly. And so it's important to launch directly into the correct orbit. So a great deal of effort and time has been devoted to the problem of establishing spaceports in geographically convenient areas. And the reason is because the orbital parameters of your orbital plane, remember, are defined by two orbital elements, specifically the inclination and the right ascension of the ascending node. So the right ascension of the ascending node is relatively easy to change. It doesn't change a whole lot with launch geometry. You just have to get the right launch window, so you have to launch at the right time. We'll address that, but by far the more important consideration is inclination. What is the desired inclination of your orbit? Now, there are many desired inclinations of the orbits. You can have a polar orbit where I is 90 degrees. You can have an equatorial orbit where your inclination is 0 degrees. You may have an interplanetary transfer or parking orbit before your interplanetary transfer, in which case your inclination is the obliquity to the ecliptic, which is either 23.5 or 22.5, depending on how my memory is working, and it's not working very well now. So I'm going to say it's 22.5. There's actually a problem in this lecture, or a numerical example, for the transition to the ecliptic, so I guess I can just go over and grab that number real quick. 23.5 degrees. There it goes. Not 22. Right. So as I said, the launch geometry determines your inclination of the orbit you launch into. So there are two parameters which you can control to some extent based on your launch geometry. So the first is, and the most inflexible, is the latitude of your launch site. So once you pick your spaceport, that latitude is fixed. And depending on your desired inclination, that may prohibit you from launching directly into your desired inclination. So that's a very important number, especially since inclination changes are so expensive. So this is going to put a hard constraint on your inclination. The parameter given a launch site, which we have some flexibility in, however, is launch azimuth. So the direction we launch our spacecraft in. So say, for example, let's see, where are we here? Where it looks like we're in Alaska or something like that. I don't know where that is exactly. We may launch this direction. We may launch this direction. We may launch this direction. And we may launch this direction. And depending on that launch direction, we can change or modify to some extent, limited, of course, by the latitude of our launch site, the inclination of the resulting orbit and the right ascension. But as I said, right ascension can be chosen fairly arbitrarily through the use of launch windows. So we're going to concentrate on the relationship between launch azimuth and its restriction, launch site, which is clearly restricted depending on which site you choose, and the inclination. That's the main focus of this lecture. So we're going to look through a couple of launch sites. This is a relatively old picture. This is from the SMAD tables. And the older SMAD, SMAD 2, came out fairly recently. So it may or may not be up to date. I think they generally call this one CSG now, Kourou. So you see here, what you see are several launch sites. These are the black dots. And what you see tacked onto each of those launch sites are ranges of azimuth, which you're allowed to launch from. Now, the reason we restrict azimuth, of course, is because rockets sometimes don't work. And if they don't work, they usually don't work in a fairly destructive and life-threatening manner. And in particular, even when they do work well, they occasionally drop nasty chemicals and various byproducts of launch fuel into the atmosphere and onto the ground. And so we typically want our rockets to launch over the ocean. And when that's not possible, say in a relatively landlocked country such as Russia or China, we prefer that they launch over uninhabited regions. So for example, we have this lovely launch site in Kazakhstan, I think it is, Kapustin Yar, which if I believe that's the dialect of Russian Kazakh, maybe, which basically kapusta in Russian means cabbage, and yar means field, so it's a cabbage field. So I don't know if people actually actively grow cabbages on that field anymore, or if it's been cleared out so that rockets can launch over it. But in any case, we have a set of acceptable azimuths, or launch directions, we can launch into. And that's given by this little sort of semi-circle here, or partial circles there. Now, as you see, it's generally desired, and we'll go into this in more depth, to launch to the east. Right? So a majority of these launch sites are pointing east for the main reason that that's the direction we want to launch because of the prograde nature of the rotation of the Earth. If we launch east, we get a little boost from the rotation of the Earth, which gives us a little boost in velocity, so we don't have to, our rockets don't have to push quite as hard. So that's the majority of launch sites, and you can see them here: Wallops, Kennedy, Kourou. These guys, the Chinese ones, all looking fairly to the east. There is exceptions to that. So the big exceptions, of course, being, say, for example, Vandenberg over here, which is pointing to the south, and these sort of Indian launch sites over here near the equator pointing to the south as well. You could have one pointing to the north. It would actually achieve pretty much the same objective. In any case, you also have these sort of south-pointing launch sites because occasionally we want to launch into those polar orbits where the inclination is 90 degrees. So the orange ones typically are into either low inclination or zero inclination orbits. So 0 degrees, 23.5 degrees for the ecliptic. Or maybe you have like GPS satellites or communication satellites which have moderate inclinations, like maybe up to 32 degrees or 60 degrees or something like that, depending on the constellation where they want to cover. By contrast, of course, then you've got the other launch sites which are pointing south, and those are almost exclusively for the purpose of launching into polar orbits. Right. So let's now take a more quantitative look at how these restrictions on launch azimuth and launch latitudes restrict our inclination of the injected orbit. So the problem that we're faced with here is one of spherical trigonometry. So we have a triangle, or it looks basically like a triangle. Here, I'll sort of outline it for you. So what we've got here are several angles. So the first is the inclination. Well, actually, let me take a step back. We are launching from this site, and we're launching in a direction which, in this slide at least, is corresponding to this line here, this arc of a circle, which is centered around the center of the Earth. So we launch in that direction, V, and of course suddenly this becomes a descending node because, okay, we're going to have to come back to this issue in just a second. And we have a spherical triangle. This is going to give us, assuming that was the ascending node, that's going to give us something like the right ascension. Not exactly, but something like the right ascension. It's going to be related to right ascension. And then, of course, the inclination of the orbit, if we were launching this direction, is this angle right here. So we have a sphere, or a shell, of radius 6378, centered on the center of the Earth. And these lines in spherical trigonometry are not lines at all, they're actually arcs. And we have to measure, we have certain angles that we can measure. So in particular, we have here the latitude, phi GC, is the latitude of the launch site. So that's this arc right here. And that is measured in degrees, right? And like, so for, if it was Phoenix, it would be 33 degrees. So that's one angle. And we have this other angle, which is not an arc, but an actual angle-looking thing, which is measured between two arcs, and that's inclination. So that's a different type of angle. We can call these sort of large A's and small A's. So a large A corresponding to a small arc. So we have those two angles, latitude, inclination. We have another one here because latitude is defined by dropping a perpendicular down to the equator. So it's measured vertically from the equator. So this little angle here is actually 90 degrees. The little angle here, we're going to call that, I believe, large C. Other angles we have, well, some of these are indeterminate. So obviously we have beta, that's a small angle. And I believe we're going to call, actually I think we call inclination B. And this one is A. So the azimuth in this spherical triangle is A, inclination is B, large angles, and C is 90 degrees. Little b is the latitude. So we have several angles on this spherical triangle. Unfortunately, of course, as you might have guessed, all of these are defined using angles, and hence, say, the Pythagorean theorem doesn't apply to these types of spherical triangles. Because, for the obvious reason, there's no lengths. Everything is defined in terms of angles. And so we have to sort of define a new set of trigonometric relationships for spherical triangles. Spherical triangles are a little bit complicated in that the sum of A, B, and C is not 180 degrees, for example. In fact, you could define a spherical triangle where just one of those angles is 180 degrees. So spherical triangles, that those interior angles do not add up to 100 degrees. And in fact, they're not even limited to be less than 180 degrees. So what we've got here now is several terms which we know. We know this arc. We know that's 90 degrees. We know the azimuth, presumably, and we know our desired inclination. So it turns out, right, that is enough information. Actually, I should probably move those back and forth, but that is enough information to determine any one of these angles in terms of the other two. And in particular, we have this simple relationship which gives a relationship between inclination, latitude, and azimuth. Right? So this is similar to the law of sines, but not exactly. So I'll actually at this point switch over to the next slide, which gives us the laws of spherical trigonometry, or what they're called Napier's rules for spherical right triangles. So a spherical right triangle, in this case, as we defined it here, is where C is 90 degrees, just because on the picture, right, on this picture up here, right, C was 90 degrees. If B isn't under 90 degrees, then you can swap out B and C and you get the same relationships. But here we've called C 90 degrees, and so we get a relationship between any two of the other angles and the third one. Right? So for example, given A and B, we can get C. Given B and C, we can get big B. And so as you see, given a right triangle and two angles, whether they're lengths or sort of arcs or internal angles, we can get the third one. Right? So that's a very useful set of rules, but there's no way to actually remember them all, of course. In particular, the rule that we're using here is Napier's 8th rule, where here B is inclination, A is azimuth, and little b is latitude. Right, so we're using Napier's 8th rule. Now, I want to take a step back to this picture here before I move on, because this is a source of some confusion. So azimuth on this picture, just because I'm trying to show off the spherical trigonometry aspect, is defined by a clockwise rotation from the southern vertical. Right, so the line pointing straight south, due south. It's measured from due south. So that if we have a set of acceptable azimuths, that makes sense. And especially if we're launching, say, to the west or to the south from, say, Vandenberg or something like that, this definition makes sense. However, it's not the one most commonly used. Right? So in particular, the one most commonly used, if you search the literature, is measured from due north as opposed to due south, but likewise in the clockwise direction. So we'll call that one beta prime. Right. So if we look at this, here I mentioned beta equals A if we're using the picture on the previous slide. Alternatively, and I give several tables listing acceptable azimuths, and you'll probably see them as well, for minimum and maximum beta. Those are measured from due north, clockwise. Right? So this is a bit of a problem. Our spherical trigonometry changes somewhat depending if we're launching, how our azimuth is defined, and whether this or this is our right angle. I've given it in the case where this is our right angle and azimuth is defined from due north, like that. From due south, like that. However, right, you can, if your azimuth is given from due north, of course, you can just add a correction or subtract a correction by you saying beta, the beta in these figures is the beta from those tables minus 180 degrees, right? So that still works. And here, just for convenience, I give Napier's rules for spherical trigonometry for spherical triangles in the case where beta is 90 degrees here, right? So I rewrite them. And this would be more the case if you were launching from Vandenberg, or from Kennedy or Wallops or someplace to the east. Right? And again, right here, this is our vertical, that's due south, and so either this is our azimuth restriction or that one, depending on whether you're using the tables or you're using the picture. So both cases listed here. Right, so let's go through the this problem a little bit more carefully. Right, so here we've got several ranges of azimuth. Right, so in here I'll just draw my picture. Here's the United States. There's the United States. There's Florida, Texas, and California is over here. Right, so Vandenberg is over here in California. And its acceptable launch azimuths, for example, are 147 measured from the vertical to 201. So that's 180 in this case, from 147 to 201. So 20 degrees plus, well, 20 degrees plus, and looks like 33 degrees minus. So a range of around 54 degrees, something like that. Likewise, if we're launching from Kennedy over here, right, we're measuring again from the vertical, so 33 degrees down. So there's 37 degrees down, all the way down to 112 there. Now, again, if we're using the definition on the previous slide, we would have to subtract 180 degrees, so we would get some negative angles here when we did that correction. So again, right, there's a range here of about 100 degrees for you to play with if you want to launch. Right, up, that's about 53 degrees up from east, or about 22 degrees down. So not as much down, but we can go up by 53 degrees and we go down by 22 degrees. Typically we launch up, right, towards the north. Right, so you can look at all of these. Let's see, where's Kapustin Yar, right? Great deal of flexibility there. Actually, looks like 100 degrees of flexibility in azimuth angle from a Kapustin Yar. And again, measured a little bit up from the vertical down to 90 degrees, so like that. That's what it looks like. This is east for Kapustin Yar. So I think that gives the general impression of what we're working with. So now let's apply these formulas I got on the previous, and actually means just go grab it so we can remember what it is. I'll just paste it here. All right. So let's just take a quick example. This is the easy one. We're launching from Vandenberg, probably for a polar orbit, something like that. Vandenberg is located at 34.6 degrees latitude, so that's 34.6 degrees. The acceptable launch azimuths are here, listed for Vandenberg, 147 to 201. Now, using the rule, this beta, we have to do a little correction. So we have to actually restrict our betas. We have to do a little correction there to our betas and subtract off 180 degrees from both of those. Right. And then we've got both of those numbers. So this one is 20.1 degrees. from 20.1 degrees to, looks like negative 33 degrees to 20.1 degrees. So you plug in those two values of beta, and we could get a range of acceptable inclinations. Obviously, your latitude isn't going to change. So we just do, we find that the cosine, right, is between negative 29.295, which corresponds to negative 33 degrees, and 0.44, which corresponds to plus 21 degrees. And so we do an inverse cosine formula on that, and we find that our inclinations, resulting inclinations, are restricted to between 63 degrees, put a little circle there, perfect, and 107 degrees. So if we just draw our spherical triangle here, right, our inclinations resulting from Landrum-Vandenberg can be anywhere between here, this 63 degrees, and if we draw the spherical triangle over here, this corresponds to 107 degrees. Right. So again, the internal angles of these spherical triangles can sum up to greater than 180 degrees. I should mention that the tables listed here, I believe, calculate, do not include a correction which you have to add to the geometry to account for the rotation velocity of the Earth. So, but I'm not absolutely sure on those numbers. So if you have a table of acceptable azimuths, you probably need to include a small correction from that little delta V you get from the rotation rate of the Earth, because I believe the azimuth angles are restricted based on the Earth-centered, Earth-fixed coordinate system. And again, they're all measured from due north, 180 degrees in the tables. Okay. So once you've fixed your inclination, right, using this formula over here, we can do the easier part of this task, which is now to determine launch geometry corresponding to an acceptable right ascension of the ascending node. So in this case, we have to be a little bit careful because to make sure that we're going in the right direction and not heading towards the descending node, which would make things a little bit more complicated. So remember, of course, if you're launching down, then this suddenly becomes the descending node. Now, obviously, inclination isn't going to change if you're at the ascending or descending node. However, if you're heading towards the descending node, this is not the correct definition for right ascension. So in this case, we're going to actually assume that we're launching in the opposite direction, right? So this figure, which I stole from Vallado, is a little bit misleading in that respect. So this is the first point of Aries. And so actually, if we were drawing this thing right, we should probably, I mean, it's very difficult to draw these obtuse angles in geometry, but if I were doing it, I would probably do it like this. So I would drop a vertical like that, do the azimuth like that, beta, and then this angle here, it does correspond to the right ascension of the ascending node. Like I say, this is still descending node. Okay, so in the northern hemisphere, we have issues with ascending versus descending node. In any case, this point, right, is determined by the time at which you launch, because the local sidereal time gives you the angle, right, that your local time makes. Here, I just crossed out local sidereal time. Actually, I'll just highlight that. Right, the local sidereal time, if you recall from lecture 7, is defined in terms of the angle from the first point of Aries to your local longitude line. Okay. And so if we're looking at this angle, we want to figure out, well, what is the desired angle as measured from the first point of Aries to here, and then we can figure out what this desired triangle is. So once we've got the triangle, remember we already have the triangle because we have I, which is here. We've got that angle, we've got that angle, and we've got this arc. So the triangle is all perfectly well defined already. So all we need to do is figure out what this is, and then figure out our corresponding local sidereal time. Right? So again, using Napier's rules of, actually I believe this is from the, you can, with this one actually, you can get either way. Napier's rules, or you can use, there's a law of sines and cosines for spherical trigonometry, which actually we're going to come back to in the part D of this lecture when we're talking about plane changes. But in any case, so in this case, we're looking for A here, right? And we've got azimuth beta there, and we've got, what else are we using? So we've got A, and we're going to use, it looks like B. Right? So we've got A, and we've got B, and big B, we've got big B, and we've also got little b, and so that's phi GC. So if we go back to this, this formula here, we've got A, B, and actually it looks like we're not using, oh, here we go. We're using, actually it looks like we're using Napier's rule. Oh yeah, sorry, see, I said it here. Where this formula actually is derived from Napier's ninth rule of spherical trigonometry, because we have that right angle. I'm not sure then why I wrote down the law of sines and cosines, but there you go. Human error, or human forgetfulness, more to the point. In any case, so Napier's ninth rule gives us this relationship between A, and B. And given any two angles, we can find the third one for a right spherical triangle. Now, of course, the laws of sines and cosines, right, they work even for non-spherical, for non-right triangles. But again, we have a right triangle here. So now we've got this geometry, which is going to give us our launch azimuth. And we can plug our launch azimuth in here, and I is already given, determined. And that's going to be used now to solve for this angle, lambda. Right? So now we have our lambda. And now we can determine our launch window by then taking our right ascension of the ascending node, desired right ascension of the ascending node, and subtracting off the, or adding the this angle here. So equals sidereal time equals this angle plus this angle. Although depending if this is your ascending, that assumes this is your ascending node. If it's actually your descending node, you're going to have to add 180 to that. Right. So determine if that's your ascending or descending node, and then add 180 if it's a descending node. Because remember, the right ascension is the right ascension of the ascending node. All right, so let's sort of put these pieces together with a relatively simple example. This is a launch from Kourou, otherwise known as the Space Centre Spatial Guyana, or I like reverse those letters, it's actually CSG, because it's French. So it's actually a French province, the French own it, so they launch all their space satellites, at least the ones for near equatorial orbit from there, because obviously Europe doesn't have very good launch windows because it would launch over populated areas. And so the Europeans tend to launch from other places. And in particular, Kourou is a very popular one. So in this case, we have some arbitrarily chosen right ascension of the ascending node at 0 degrees. We have a desired inclination of 23.5 degrees, the ecliptic. And the question is, what's our corresponding launch azimuth and launch time? And then particularly answer the question of whether that launch azimuth corresponds to one of the acceptable ranges of launch azimuth. So if we look up Kourou on the tables, I'm gonna here on the tables. Where's Kourou? There's Kourou. Right. So the range of acceptable launch azimuths is 340 to 100 degrees. Just go over here. So 340 to 100 degrees. Right. Now, because that table measures things from due north, I'm going to add or subtract 180 degrees to this to get it in the format that I used on the previous slide. So in this case, I'm adding 180 degrees here and 180 degrees here, or I can say I'm subtracting 180 degrees and then normalizing, whichever you prefer. So minus 180 plus 360 basically. And then I get a range of azimuths in my desired format from 160 to 280 degrees. So if we just draw a little picture here, by the way, of course, one of the reasons that Kourou is, or Space Center Guyana, is so popular is because it's almost on the equator. It's in Equatorial Guinea, hence the name equatorial. So here we are at a very low latitude and an acceptable range of azimuths from 160, right? So 160 is like up-ish, right? Because here these are measured from due south. 160 to let's see, all the way to 180, and then 100 degrees beyond it, so down there. So again, from north, they're 100 degrees, not 1,000 degrees. So from due north, it's 100 degrees to negative 20 degrees, depending on which version of azimuth we're using. Anyway, so that's the picture. Obviously, we're going to launch to the east. That makes sense, right? So we're going to launch in that direction. And the question is, can we launch directly into an inclination of 23.5 degrees? So 23.5 degrees, desired inclination, right? Here, I'll just remember my formula from the previous slide. Actually, there was another formula. I should grab that as well. Other formula as well. Right. And so, right, 23.5 degrees. Well, I've got it right here. This is 5 degrees, 5.2 degrees. And this one is indeterminate, right? So we have to solve, first step is to solve for beta. What is our azimuth that we need in order to achieve inclination of 23 degrees from a latitude of 5 degrees? So if we just do inverse sine on this, this formula, this is what we get. Remember, inverse sine has two solutions, and so we write down both of them. The first is 67 degrees, and the other is 112 degrees azimuth. Now again, these are measured from due south, right? So we're going to have here that, and we'll have that. So those are our two azimuths. And you may notice that they look kind of like they're going in the wrong direction because we want to launch to the east. So actually, we'll take those two azimuths and add 180 degrees to get them in a prograde orbit. Right? So we'll add plus 180 degrees to that and plus 180 degrees to that. So that's mentioned here, right? We're looking for a posigrade orbit, so we're going to actually go the other direction. And which of these is going to work? We don't know, right? So we will check both of them. Let's start with the 67 degrees. Let's start with that one. I'm going to skip the right ascension for a moment. I'll come back to it in a second. So let's try the first one. We add 180 degrees to it, and we get a required azimuth of 247 degrees. And we compare that to our acceptable range of azimuths, right, which is 160 to 280. And so a prograde launch out of Kourou at 67 degrees beta plus 180 degrees to go prograde is going to be acceptable. We can also check the other one, 112 degrees. In this case, we add 180 because we also want to be going prograde. That gives us a launch azimuth of 292 degrees. Again, these are somewhat unwieldy because they're measured from due south. They're going all the way around. Unfortunately, that's not acceptable because I guess it goes too close to the African coast, or the South American coast. Sorry about that, South America, or sorry about that, Africa, depending on which you prefer. And so launching down prograde is not an option. So that was also an option, right, in our spherical triangle. There are basically 4 solutions, right, for any desired inclination: prograde, prograde, retrograde, retrograde. Right. So we're launching prograde. So we have one option that is acceptable within the azimuth window. Next, we can finalize this orbit by calculating the corresponding local sidereal time. We don't have to do any corrections because we're launching prograde. That makes life a little bit easier so this point down here is going to be the ascending node, so that makes our life a bit easier. We solve this formula here. We've got I now. Now we've got beta as well. So we just plug in those 2 numbers here. Beta is 67 degrees, inclination 23.5 degrees. And so we get a local sidereal time, or desired local sidereal time for launch of 12.07 degrees. Because remember, our right ascension is 0. If right ascension was not, we would have to add something to this. So we would add... So if we had a right ascension, we would have to add the right ascension to that local sidereal time. So that's pretty much it. It's not terribly complicated. Well, it is, I guess, because there's like 4 different ways you can launch to get into a single inclination. And so you just sort of figure it out. And there's 2 definitions for azimuth. So again, spherical trigonometry, rearing its ugly head. Here's just a nice picture from a prograde launch. Again, right, I could pull that back. We could launch retrograde. In this case, of course, we're measuring, there's our spherical triangle, and we're using the B equals 90 degrees here, right, for the alternative. And again, this is an arc here. It's a relatively large arc. It's more than 90 degrees, obviously. Right, so again, right, here's a more modern listing of these angles. Look at these tiny little azimuths. These are obviously very specialized launch windows in Chinese territory. This is clearly just for low inclination orbits, and these are for polar orbits. Right. Okay, so at this point I will stop and come back next time to what happens if you launch into the wrong orbital plane, or you just want to make an orbital plane change for some reason or another. Again, only 9 slides on that, so hopefully it should be done rather quickly.